Suppose f of n and g of n are complexity functions, and the limit as n goes to infinity of the quotient exists. Then, if the limit is a non-zero positive real number, g of n is order f of n. If the limit is 0, the order of g of n is less than the order of f of n. If the limit is infinity, then the reverse is true. And in general, if the order of g of n is less than the order of f of n, we regard the algorithm requiring gn steps to be faster than the algorithm requiring f of n steps. We also found that if f is a degree k polynomial, then f of n is order n to the k. What about transcendental functions? Let's compare log n to n to the p, where p is something greater than 0. We find the limit as n goes to infinity of the quotient is, we'll apply L'Hopital's rule and find, since we're assuming p is greater than 0, this limit will be 0, and so the order of log n is less than the order of n to the p. Consequently, logarithmic functions grow more slowly than any power function. Likewise, for p greater than 0, if we find the limit as n goes to infinity of the quotient, we find, consequently, exponential functions grow faster than any power function. Now, we often encounter products of complexities, for example, n log n or n cubed e to the n. Where do these fit? Well, let's compare n log n with n to the k. So we want to find the limit as n goes to infinity of the quotient n log n divided by n to the k. Now, we can simplify the n and n to the k part, but what that simplification looks like depends on the actual value of k. So note that if k is greater than 1, this expression will be, and after a L'Hopital visit, we find so that tells us that the order of n log n is less than the order of n to the k for any value of k greater than 1. On the other hand, if k equals 1, the limit as n goes to infinity of the quotient will be, and so that tells us that the order of n is less than the order of n log n. And likewise, if k is greater than 1. And so that tells us that the order of n log n is between the order of n and the order of n to the k for any k greater than 1. Note that this means that an algorithm that takes n log n steps should be regarded as slower than any algorithm requiring n steps, but faster than any algorithm requiring n to the k for k greater than 1. So for example, let's compare 2 to the n and e to the n. So again, we might find the limit of their quotient. Now, we could try a visit to L'Hopital, but we won't for 2 reasons. First, nobody remembers the derivative of 2 to the n, and second, it wouldn't help us anyway. Instead, we'll do some algebra using the fact that the quotient of powers is the power of a quotient, and since 2 over e is less than 1, and so the limit as n goes to infinity of the quotient is going to be 0, so the order of 2 to the n is less than the order of e to the n. This gives us an ordering which we might describe as the order of log n is less than the order of n to the k, which is less than the order of a to the n, for all k greater than 0 and a greater than 1. Moreover, if k1 is less than k2, then the order of n to the k1 is less than the order of n to the k2, and the order of n to the k is less than the order of n to the k1 log n, which is less than the order of n to any greater k. Finally, the order of exponential functions is going to be determined by the order of their bases.